if one wanted to oversimplify the course to electricity and magnetism to Maxwell's laws, which would be okay to say, Gauss's laws are two out of those four equations. And Gauss's law, at least for electricity, boils down to Coulomb's law. And as we'll see, Gauss's law is better. It's relativistically correct, whereas Coulomb's law isn't, mainly because it's stuck with distance and time. And so you have some issues there. But let's get into it. So today we'll introduce Gauss's law. Wednesday, we'll start a boatload of calculus problems using Gauss' law. And that probably will extend into next week. So I haven't made any assignments for this week. We needed to be flexible and kind of run it a little bit different for a while. So more on that later. So don't sweat the assignments. So let's get here. So these pictures, the big idea with Gauss's laws is Gauss thought of things differently, thought in terms of electric flux. And so now Faraday would be the first person, if you remember the movie, he imagined invisible lines of force emanating from these charges that were moving, et cetera, et cetera. And now Faraday didn't even come close to having the mathematical background to do what Gauss and Maxwell could do, but he had the right imagination. And so field theory has been fantastically successful feature of physics for over 100 years. So for more than a century, that's worked really well for us and is foundational to modern physics. But so he imagined, well, if I enclosed a source of charge in a imaginary surface, because imaginary surfaces are wide open to be exploited by mathematics. So you have enough calculus background now to realize, oh yeah, surfaces, we can do a lot of calculus stuff if you have a surface. And if there are simple surfaces, it gets easier to do that. And so the idea of Gauss's laws is to do surface integrals on a surface that encloses electric field lines. And so what you have, either you have electric field lines coming out of some surface, into some surface, or through some surface. And two of those things mean that there's a charge inside of your fictitious box, and one of them means that there is no source charge. Okay? And lines of flux meaning how many things are going through an area. So if we had a hula hoop and we were throwing ping pong balls through it, there would be a ping pong ball flux through that circular area. Just flux. Not to be confused with the soldering stuff. Maybe solders with. Who's ever soldered? Who doesn't have any idea what I'm talking about? All right, never mind. So if you have electric field lines coming out, and they're only coming out of the surface, they're never going through the surface. The only way you could do that is if there's a positive charge inside of your box. There's no other way to pull that off. If it's the case that everything that goes into your surface comes out of your surface, then there's no charge in there. The gazentas equals the gazoutas. There's no charge there. It's just a region of space that has electric field lines in it, but no source of electric field lines. Right? So there would be no charge in that space, just the same field going in as comes out, net of zero, if you will. And then the last one, if everything's going into the surface and nothing's coming out, the only way you could do that is if you have an electron or a negative charge in that Gaussian surface. Now there's we don't really make Gaussian surfaces. I mean, you could enclose a charged source in some sort of sphere or box if you wanted to, but the idea of these Gaussian surfaces is they are mathematical devices that we let us do calculus. So we've done a little bit of calculus for Coulomb's law stuff, and now we're going to show Gauss's law, basically give you back Coulomb's law, but in a slightly different form. And in many ways a simpler approach, and one that a bit more physical, as you'll see shortly. So that's the big picture of Gauss. What is Gauss doing? He's paying attention to flux, originating from, terminating in, or entirely going through some sort of surface that's integrable, if you will. All right? So let's deal with this. I'll give you a chance to write, draw your pictures and whatnot. So this box here, all right? And let's say that, let's just look at one field line coming out of the box. And this would be a repeat of the previous page where it was only, there's a positive test charge in this box. But we're going to pay attention to one piece of this puzzle. And so this electric field line is coming out of the box at an angle to what would be called the normal of that area. So this n hat vector, okay, is perpendicular to the surface on this side of the aisle, okay? And what we're going to do, and it will make more sense here in a minute, is we're going to treat the surface area as a vector. I don't know if you've bothered to do that in your other courses, but we can pretend that the surface area is a vector, and it is always, the surface area normal is always perpendicular to that surface area in that patch. So if it's a sphere, it's a little bitty patch, and I have a region of that patch, if it's small enough, which it is when you have a differential, that it's perpendicular to that. All right? And so now the electric field will either be parallel to that or it won't. If it's parallel to it, then that's easy. We don't have any components to deal with. But if it's not parallel to it, it's at some angle, then we have to deal with a cosine or something to do that. And then we end up getting to a dot product. And the reason for that we use a dot product is dot products produce a scalar quantity, all right? And that's what we're going to be dealing with here. And so get some things out of the box here, and then I'm going to do a different derivation here in a little bit. So there's some portion of the electric field that's parallel to the surface area, the normal of the surface area. So it's a weird thing. I have electric field lines, some of which will be perfectly perpendicular to the surface area, and some of which will not be. All right? If it was a sphere and the charge was exactly in the middle of the sphere, then every field line would be perfectly perpendicular to the surface area. But if it was off-center, then it wouldn't be, and that would be measurable. That would show up in your math, right? So, but the idea that admittedly is weird is this: we use a normal vector that we'll call n hat to geometric surfaces as a way to represent the direction of the surface area at that point. But the surface area isn't going anywhere. The electric field is. Okay, but it doesn't matter in the mathematics. This is physics, math, reality thing. We're using the flexibility of mathematics, okay, to be entirely unrealistic and unphysical, but yet give us a tool that lets us pay attention to the physical. Because we're not even talking about a real surface. We're talking about a mathematical surface. and we're giving that surface, its area, a direction. And that direction of that surface area stands in some sort of relation to the direction of the electric field going through it. Okay, so textbooks, I've not read a textbook that really explains that in detail. Textbooks tend to abbreviate things a bit too much. All right? So your book, every other book has the same basic shortcoming in that regard. Otherwise, you need a wheelbarrow for the 12 volumes of your physics book that said every possible thing that could be said. You need 5 years to take the course. All right. So let's get down to this dot product business. So we have this statement here that's currently unjustified, and I'm about to justify it. Is that, well, mathematically it's totally justifiable, so I just want to pay attention to just the math. Okay? Even though it's about some physics, let's just think about the math. If I have a dot product of two vectors, which the dot product is designed for when you have two vectors that stand in some sort of relationship that produce a scalar quantity. Dot products give you a number, cross products give you a vector. So work, force times distance, is a dot product because energy is a scalar quantity, not a vector quantity. Torque is a cross product because you get another vector out of these two vectors that go together. So it absolutely is the case that when you do a dot product, it's always the magnitude of the two vectors times the cosine of the angle that's between them. That's the definition of the dot product. Every time. Your cross product is similar, except it involves a sign and it maintains a direction. So let me insert something to this. So if we go back to that, we're basically the magnitude of that surface area vector times the cosine of the angle between it and the electric field gives us this nice thing. And so one of the things that will make it easy, and you'll see this when there'll be a problem we're going to do here in a little bit. If things are going outward, +1 is what your unit vector is if it's going out. And it's minus if it's inward going. And it would be 0 if it's just passing through. There would be no charge enclosed in that. All right? Lecture here. So, electric flux. Let's talk about electric flux. It would just be the number of electric field lines per unit area. That would be a simple way to describe what we mean by electric flux. And I described that earlier with the hula hoop and throwing ping pongs through it. There'd be a ping pong ball flux. Or if you were shooting arrows through a hoop, there would be an arrow flux. How many arrows went through that in that time interval? Okay? Flux. How much stuff per unit area? Flux is always even though you might be talking about what's going into or out of a volume, when it goes through the Gaussian surface, it's going through an area that encloses that volume. Right? So let's some reminders here. So since we're dealing with electric field lines, remember that the electric field is defined as Q per R squared, and I'm going to put R hat for the direction of the electric field. The direction of the electric field is along the line between the source and the location, the observation locations. So R hat works just fine for that. Now, one way to think about the electric field, and this is thinking about it, so this is a Coulomb viewpoint. A very Newtonian way of looking at this force interaction. All right? But the way to look at the electric field from a more modern viewpoint, from a kind of a Faraday viewpoint, or now Gauss, is the number of flux lines per unit area. So we like to use this symbol. This is a capital, it's the capital phi, I believe. Whatever that symbol is. It's not a theta. I'm pretty sure it's phi. Space right out of my head there. Flux per unit area. And to be consistent, it would need a direction. Same direction as the electric field. This is a different viewpoint, but it's taking seriously what Faraday originally observed that you saw in that docudrama, and then other people picked up on Maxwell, Gauss, etc. All right, so this picking up on this flux thing, all right, and excuse me, running with it. So what that means is, so this is our Gaussian viewpoint. What this boils down to is that flux can be written as the electric field times the area. Now I left them as magnitudes, okay? Because I just, if anytime you just talk about a magnitude, you just drop the unit vector, and now you have a magnitude. And that's the definition of a vector. So we were able to define flux mathematically. So we have a visual idea of what we could imagine, and if I apply it to the electric field, I get that flux is the electric field strength times the area that those electric field lines are passing through. Okay? Now, it is the case the surface area of a sphere is 4 pi r squared. Hope you recall that. So I have this kq per r squared r hat, and that equals this flux per area r hat. Well, k is 1 over 4 pi epsilon naught. I'm going to drop the r hats. And the area, if I'm talking about a sphere, which is our preferred one for most what we're going to do initially here, is 4 pi r squared. So we saw these r hats go away, 4 pi drops out, r squared drops out, and what do we get out of this? We get that we have a q per epsilon naught equals this flux thing. And we also know from our previous thing that flux can be thought of as electric field times this area. And if I give the area a direction, then my area becomes a vector as we've notated on the prior page. Okay? So there's that. Now this next thing. box 1, let's just imagine it had one positive charge. Same box, in the bottom part, the electric field's bigger. I must have 2 charges. Okay? So we're using these vectors as indications of strength. So the length of a vector arrow is, by definition, indicative of its magnitude. Longer arrows have a bigger magnitude than shorter arrows. All right? Then that would be the thing. We don't use graphical vectors as much. We stick with the numbers, but from a representational standpoint, the magnitude would have to be consistent. So it's just a little side note. However, if you change the size of the box, you get less field strength at the surface, okay? Because you're farther away, right? Coulomb's law. R gets bigger, so if my box gets bigger, R gets bigger, strength of the field at that point is smaller. Basically, how much is sticking out, okay? Because you're farther away. Pretty simple. So I'm not going to labor on all of that too much. Let's get into some of the, I guess, an algebraic viewpoint of these little patches of area. So we're going to shift from accepting that the flux is equal to electric field times area, and that both, obviously, electric field we already knew was a vector quantity because it's directed, and the A, we're deciding to direct it. We're deciding to give the surface area a direction. And the reason we can do that is because then the dot product tool becomes a useful tool. So, I mean, this is just math wizardry. This is sorcery, witchcraft, all right? We're doing this on purpose because math lets us, all right? Uncanny effectiveness of mathematics to describe stuff. So, I think you're pretty familiar by now, at least I hope you are, you better be, that I can always think of little bitty patches of area, okay, like we're doing here, and that's going to get us to a differential on area, which is what we're aiming at, to do calculus on this, right? And if I did all of those little delta A's, which are going to be defined as a delta X times a delta Y, little square patches, okay? If I added all of those delta A's up, so an integral would be a nice way to add up little chunks of stuff, okay, differentials, chunks, then I can describe these things in this fashion. So let's take this was supposed to pop out in stages, but it didn't. These lines here were supposed to not come out all at once. So let's zero in on this right here. There's 2 ways to look at this situation. So if you look and you see that, all right, I have this little chunk of area, so this right here is, you know, one of those. So we pulled it out, set it up, and almost making it 2-dimensional so that we can pay attention to the math here. So this little chunk of area from up here, and I have my electric field coming out of it at an angle to the perpendicular, meaning this normal vector, angle theta. So there's a portion, you know, this vector here is the projection of the actual vector down onto the perpendicular to the surface. Okay? And so E perpendicular, okay, this right here, basically I'm the part of E that's perpendicular to the surface. Right? This notation. And then the flip side. What if I lean back a surface and I talk about lean it back so that the electric field is perpendicular now to something, but now that stands in a relationship to the actual Gaussian surface. So 6 one, half a dozen the other. All right? This little minutia isn't going to be as critical for the problem solving. In fact, it's almost irrelevant to most problem solving, but it just depends on what problem we're trying to solve. Most of them we don't have to really worry about it. Just worth exploiting the mathematics here a little bit. All right, so here let's get to some definitions of things. So we're heading towards this Gaussian law piece of the puzzle. So we do define flux this way. And the trick here is, how do you, when you read that statement, you know, how is this the same as, you know, the number of, you know, electric field lines per unit area? I mean, that's what I said initially. And so the challenge for you, and a great way to make space go away in your learning outcomes essay, is to articulate how that formula and the geometry that's been shown here, and you'll find it in any university physics textbook, basically encodes for the number of electric field lines per unit area. Should be easy, it's a sum, and we've we've given the area direction, so there's some pay dirt for explaining stuff in here. So we go from, you know, this definition, which is in the form of a sum, and so now our sum becomes, you know, an integral. That's the way we do it in calculus. All right, and we put a differential on the area. So we sort of worked that out on the previous screen, because that's the thing that we need to add up. Duh. So integrals, when you add up something, the differential is the thing that's you're adding according to. Those your limits are defined in those things, et cetera, et cetera. So that's kind of old school, should be relatively simple calculus for you. And here I go through the motions of what I showed you earlier. Okay, so let's notice here that right here, E, okay, we knew that from our previous work. All right, and the area, if it's a sphere, has that. So this is just a cleaner version. I just remembered I forgot to send out the notes pages. Sorry about that. Turn in late. And they end up canceling out. So over here, you know, our 4 pi and our r squared drop out, and you get this thing that we already obtained. All right? And we've already defined that. So this whole line down here on the bottom, this right here is ultimately the algebraic version of Gauss's law, and throwing this part onto it basically is the calculus-based version of Gauss law, which is a surface integral. Eventually we'll talk about a differential form, partials and all that jazz. That's later. In fact, we're going to come back, we're going to do Gauss, and then we'll get into circuits, and we'll come back to Gauss for magnetism, kind of bring it full circle. All right, so his law applies to both electricity and magnetism. We're just going to do the electricity part of Gauss, get into circuits, and then come back and do the magnetism part of it. All right. Want to can just kind of I'm going to put some extra stuff here, so if I can fit it, yeah, I can fit it. So if I have a little differential chunk of flux. Okay? I could write that as E dot dA. So all I'm doing here is I'm taking flux equals EA, the thing that we worked out previously, okay? And I'm doing the differential part on it, okay? And I'm putting it into a dot product. So I did two things. I put it into a dot product and I made it differential, all right? So I have that thing going for it. So that means if I were to integrate, flux would just be the integral of these two vectors, these two EDA vectors, if you will. And of course, if you're talking about a dot product, then you're talking about magnitudes being multiplied together. So every dot product means do the magnitude cosine of the angle between them. Okay. Here we don't have a cosine of the angle between them. It's 1 because the angle between them is 0 in this case. So we end up getting flux equals just EDA, which means flux is E because the magnitude of that is constant, and then I have to add up things according to these little chunks that I'm dealing with. Well, that's simple. You're just going to get EA like we had before. That was one of the first things we rolled out. So there's a lot of ways to come at it, if you will, but just in case it doesn't show up later, I guess the shortest, sweetest statement would be this surface integral, and so the surface integrals often will be written as a single integral symbol through a circle or a double integral through a circle. You'll see both notations. They mean the same. Technically, this one should mean a path integral, whereas the double one means an area integral, but we do that. And so the surface integral of the vector product, EDA, is defined to be the charge enclosed. I'm going to have to move my box around here. Charge enclosed over epsilon naught. So that's, I guess, the shortest, sweetest version of Gauss Law. And of course, the ways that I can write that integral ultimately is just EA. Now, remember, this is the charge, let's think of big Q enclosed, that's what the E and C stands for, in a ratio with a fundamental constant of the universe. Okay? And so we're saying that the sum of these electric field lines over the whole surface is charge enclosed per unit, this property of space that lets electric field lines go through it. So another way to look at this, and I'm going to add a big I'm kind of out of room here. Well, I'll put it down at the bottom. What this is saying is that I could look at charge as this EA epsilon naught. So, warning, this is just the bad professor swerving off the path and taking a tangent little thought experiment to kind of rock the world of your mind about what do we mean by charge. So charge isn't a substance. Charge is something associated with substance. Charges move, and electrons move and they have charge. Okay, but if I rearrange this formula and try to make sense of the mathematics, one interpretation of this thing called charge is electric field area and the property of space to allow the transmission of electric field lengths. So one weird and difficult question to answer is, what is charge? Aside from the standard definition that, okay, one fundamental unit of charge is 1.602 times 10 to the minus 19 coulombs, blah, 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 blah. But what, okay, that's a statement of fact, but what is charge? What is it? You know, what is energy? What is mass? There are people, theoretical physicists, who will spend a career investigating questions like, what is mass? What is charge? What is energy? Because we're very successful with the mathematics and measurement of this stuff and predicting it, but we're still wondering what it is. Some of these things. What is time? We're still trying to pin that down. And it's like nailing Jello to a wall. So in spite of having a fantastically successful program of physics that has produced all the stuff you take for granted, we're still wondering, it's called fundamental physics. And people with PhDs and whatnot in physics sit there and wonder about these things. And they come up with some really crazy ideas. And every now and then, one of those crazy ideas is actually fruitful. Most of them aren't. But every now and then, one of them really is. So they are just a little no extra charge for making you wonder what is charge really, if I were to rearrange it and make sense of the mathematics. Okay? So mathematics often gives you unreal, let's see, all right, things that work fantastically well. All right, let's do a problem. So in this example, there's an electric field poking out of this surface, a cylinder. So what's going to change in this is what is the area of the surface that you're dealing with. If we're using a sphere, it's one thing. If we're using a cylinder, it's another thing, et cetera, et cetera. All right? So if we give this can these dimensions of 5 and 15 centimeters, and this constant magnitude at the surface of 550 newtons per coulomb. And they're all pointing radially outward from the can. All right? Somehow, we'll ignore the caps on the ends. So, but find the amount of charge enclosed by the surface. So, right here, I have, here's my E and here's my A. So remember, flux is defined to be EA. So we're talking about the flux on the side. Just going to make our lives easy for the moment. And since it's the flux on the side, then the area I have here is 2 pi r h. Well, really, 2 pi r, that's the circumference of the circular top. That's just the side of a rectangle. So imagine if you cut a seam vertically down this cylinder. Okay? The width of that, you'd have a rectangle. So you cut the caps off of a can, cut it vertically, you lay it out, you have a rectangle. That's all, the side of a cylinder is just a rectangle. And it happens to be that the height of that, or one of the dimensions of that rectangle, is the length of the circle that was formerly constraining it to be a cylinder. So 2 pi r h is just length times width. Right? We did a lab on that sort of thing last semester. So easy peasy. The field strength, 550 newtons. 2 pi r h, just plug in Chugvilles, and we get this value of 26 voltmeters roughly, okay, for our flux. Out of the bottom, well, we didn't have anything coming out of the bottom, so it's 0. And same would be true for the top. So now what we can do is, since my EA, remember, this right here is equal to that, which means since I've quantified this, I can just rearrange this thing here, because E sub naught is a fundamental constant, 8.85 times 10, oh there it is, 10 to the minus 12. So inside of this box is almost a nanocoulomb, tenth of a nanocoulomb, if you will. Not a lot of charge inside of the box. You're thinking, okay, that's great. What would I use this for? Well, charge, well, look at all of these lights. Look at this computer that I'm scribbling on. Look at every piece of electronics that you use. It's because charge is moving. All right? And so if we want to know something about how much charge is in a location, then we need to have some sort of device that fakes a Gaussian surface, and based on the field strength that's measurable at some distance, come up with how much charge is there. Right? So electrical engineers, physicists that deal with this area of stuff, you will create a device that somehow models a Gaussian surface without actually being one. Okay? So that was a kind of a simple way to get how much charge is on the inside of a box like this. And this is a repeat of old stuff, so we have that going for us.